Right now, roughly 170 astronomical units from Earth, a spacecraft built before the invention of the personal computer, is running out of power. Only 2 science instruments still function. Engineers are preparing a last-ditch maneuver they have nicknamed the Big Bang, just to buy it a few more months. Within a decade, Voyager 1 will go permanently silent. Most people assume that is the end of the story. It is not. After the last signal fades, the spacecraft keeps moving at 38,000 miles per hour through interstellar darkness, aimed at a dim red star it will not reach for 40,000 years. The real question is not where Voyager 1 is now. The real question is where it will be when no one is listening anymore. If stories about the farthest things humanity has ever built give you chills, consider hitting that like button and subscribing so more people can find this channel. It genuinely helps, and it means the world to us. Now, get yourself comfortable. Let's begin. Somewhere beyond the orbit of every planet you have ever heard of, beyond the icy rubble of the Kuiper Belt, beyond the last measurable gust of solar wind, a machine the size of a small car is still alive. It weighs less than a grand piano. Its main antenna is a dish about 12 feet across, pointed back at a planet it left nearly half a century ago. It has no camera running. It cannot take a photograph. It has not taken one since 1990, when engineers commanded it to turn around one final time and capture that famous pale blue dot image of Earth from nearly 4 billion miles away. The cameras were shut off that same year to save power. That was 36 years ago, and power is the reason we are telling this story now. Voyager 1 launched on September 5, 1977, from Cape Canaveral, Florida, riding a Titan IIIe rocket into the sky during a window of planetary alignment that occurs only once every 175 years. The mission was supposed to last 5 years. It was designed to fly past Jupiter and Saturn, study their moons and magnetic fields, and send back the best images humanity had ever seen of the outer solar system. It did all of that before 1981. Everything that has happened since is overtime. Everything that is happening right now, this very second, is a spacecraft running on borrowed time, borrowed power, and borrowed luck. As of mid-2026, Voyager 1 is approximately 170 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, roughly 93 million miles. Multiply that by 170. The spacecraft sits more than 15.8 billion miles from our planet. Light itself, the fastest thing in the universe, takes over 23 hours to travel from Earth to Voyager 1. A command sent from Mission Control this morning will not arrive until tomorrow. The reply will not return until the day after that. Every conversation with this machine is a 2-day round trip conducted at the speed of light. That distance is extraordinary. But the distance is not what is killing Voyager 1. What is killing Voyager 1 is something far more mundane: heat. The spacecraft runs on 3 radioisotope thermoelectric generators. These are not batteries, they are not solar panels. They are small canisters containing pellets of plutonium-238, a radioactive isotope that generates heat as it decays. Thermocouples inside the generators convert that heat directly into electricity. There are no moving parts, no chemical reactions, no combustion. Just the slow, steady, irreversible decay of radioactive material producing warmth, and that warmth producing current. When Voyager 1 launched in 1977, its 3 generators produced a combined 470 watts of electrical power. That is roughly enough to run 4 household light bulbs, an entire interplanetary spacecraft, its computers, its radio transmitter, its science instruments, its heaters, its gyroscopes, all of it powered by the energy equivalent of a few light bulbs. The engineering is breathtaking. It is also the reason the mission has an expiration date. Plutonium-238 has a half-life of 87.7 years. That means every 87.7 years, half of the remaining plutonium decays into non-useful byproducts. The power output drops accordingly. Not suddenly, not in a cliff. Gradually. Relentlessly. About 4 watts less every single year. 4 watts per year does not sound catastrophic until you realize the spacecraft was only generating 470 watts to begin with. 49 years into the mission, The generators now produce somewhere around 250 watts. That is roughly half of what they started with. And 250 watts is not enough to run everything. This is where the story of Voyager 1 becomes a story of triage, of impossible choices, of engineers on Earth deciding, one by one, which pieces of a spacecraft 15 billion miles away can be sacrificed so the rest can keep breathing. The shutdown started earlier than most people realize. The first instrument to go dark was the photopolarimeter, switched off in 1980 because of degraded performance. But it set a precedent. Instruments could be turned off. The spacecraft could lose a sense organ and keep functioning. Over the decades that followed, the losses mounted. The cameras were shut off on February 14, 1990, not because they failed, but because there was nothing left to photograph. Keeping them powered would have been a waste of precious watts. The infrared spectrometer went dark in 1998. The ultraviolet spectrometer followed. The plasma science instrument was turned off in 2007. Each shutdown was a calculated death, a deliberate amputation. Engineers studied the remaining power budget, identified the instrument that contributed the least science relative to its energy cost, and pulled the plug. Every time, the spacecraft survived. Every time, the data became a little thinner. The picture of interstellar space became a little less complete. But Voyager 1 kept going. Then came 2024 and 2025, and the shutdowns accelerated. In February 2025, the cosmic ray subsystem was turned off to save power. This was one of the instruments still returning valuable science about the high-energy particles that permeate interstellar space. Its loss was felt immediately by researchers who had relied on its data for decades. On Voyager 2, the low-energy charged particles experiment was shut down in March 2025, and the plasma science instrument had already been turned off in September 2024. The twin spacecraft were being stripped down in parallel, each one losing capability month by month, like two aging patients whose doctors must decide which life support systems to disconnect first. By early 2026, Voyager 1 had 3 science instruments still operating, 3 out of 10. The magnetometer, which detects the magnetic fields that thread through interstellar space. The plasma wave subsystem, which listens for interactions between charged particles and plasma waves in the space between stars. And the low-energy charged particles experiment, which measured ions, electrons, and cosmic rays from both our solar system and the broader galaxy. 3 instruments. 3 windows into the unknown. Then February 27th happened. On that date, Voyager 1 performed a routine roll maneuver. This is a standard procedure. The spacecraft periodically rotates to calibrate its instruments and maintain the correct orientation of its antenna toward Earth. It has done this thousands of times over nearly 50 years. But this time, the power levels dropped unexpectedly. The dip was enough to alarm engineers at JPL in Pasadena, California. They knew that any further decline could trigger the spacecraft's undervoltage fault protection system, an automated safety protocol that would start shutting down components on its own to protect the probe. If that happened, recovery would be difficult. Sending commands takes a full day. Receiving confirmation takes another full day. Diagnosing a problem on a spacecraft that old, that far away, with that little power margin, under automated fault protection, would be a nightmare that could last months. The team at JPL had faced this kind of terror before. In late 2023, Voyager 1 stopped returning usable data entirely. For 5 agonizing months, the mission hung by a thread. Engineers eventually found a way to bring it back, but the crisis laid bare just how fragile this spacecraft has become. That crisis deserves a closer look, because it reveals what it actually means to keep a spacecraft alive at the edge of the solar system. On November 14th, 2023, Voyager 1 stopped making sense. The data stream that had flowed from the spacecraft for 46 years suddenly turned to gibberish. Not silence, gibberish. The spacecraft was still transmitting, the deep space network was still receiving, but the information arriving at Earth was a repeating pattern of ones and zeros that contained no usable science data, no engineering telemetry, nothing that the mission team could interpret. It was as if the spacecraft had forgotten how to form a sentence. The problem was traced to the Flight Data Subsystem, the FDS. a computer built in the early 1970s with roughly 69 kilobytes of memory. For context, the device you are using to watch or listen to this right now contains millions of times more memory than that. The FDS collects data from the science instruments, packages it into a format the radio transmitter can send, and feeds it to the antenna for broadcast back to Earth. When it failed, Voyager 1 could still receive commands and orient its antenna. Its instruments were still gathering data, but the data had no way to get home. Engineers at JPL began diagnosing the problem, but every diagnostic step took 2 full days. Send a command, wait 23 hours for it to arrive, wait for the spacecraft to execute it, wait another 23 hours for the result to return. A single question and answer cycle that would take 5 minutes on a desktop computer took nearly 2 days across interstellar distances. Over weeks and then months, the team narrowed the fault to a single corrupted memory chip inside the FDS. About 3% of the chip's memory had become unreadable, and that 3% happened to contain a critical portion of the code the computer needed to package telemetry data. The chip could not be replaced. There was no repair crew to send, no software update could be uploaded to fix hardware that had physically failed. The chip was dead, and it was taking the mission with it. What happened next was one of the most remarkable feats of remote engineering in the history of spaceflight. The team at JPL could not fix the chip, but they could move the code that had been stored on it. They broke the affected software into smaller sections and found unused memory locations scattered across the FDS where those sections could be stored. It was like discovering that a page had been torn from a book and then reconstructing the text by writing individual paragraphs on napkins, sticky notes, and the margins of other pages, except the book was 15 billion miles away and you could only turn one page every 2 days. The process took months. Each relocated section had to be tested individually. Each test required the agonizing 2-day round trip. But on April 20th, 2024, Voyager 1 began transmitting coherent engineering data again. On June 13th, science data resumed. The spacecraft was back. 5 months of silence ended by engineers reprogramming a computer built before the first Star Wars film was released, across a distance that light itself needs nearly a full day to cross. That rescue bought time, but it also exposed a truth the mission team already knew. Voyager 1 is operating on hardware that is nearly 50 years old, in an environment it was never designed to endure for this long. Every chip, every capacitor, every solder joint has been bathed in cosmic radiation for half a century. The next failure might not be fixable. The next corrupted chip might contain code that cannot be relocated. The next anomaly might trigger a cascade that no 2-day diagnostic cycle can unravel before the spacecraft protects itself into a configuration the team cannot recover from. The margin between survival and permanent loss is measured in fractions of a watt and fragments of memory, and that margin shrinks every year. After the February 2026 power scare, the team decided they could not risk another uncontrolled drop. On April 17th, 2026, they sent a command to shut down the low-energy charged particles experiment. The signal left Earth, travelled for nearly 24 hours at the speed of light, and arrived at a spacecraft so far away that by the time the command was received, Voyager 1 had already drifted another 1.4 million kilometers farther into space. The instrument went dark. It had been operating almost continuously since 1977, nearly 49 years of uninterrupted service, measuring the charged particles that fill the void between stars. And now it was silent. The shutdown was not entirely permanent in principle. The instrument's tiny half-watt stepper motor was left powered, which theoretically allows the device to be restarted later. Stamatios Krimigis, the principal investigator for the instrument, noted that the stepper motor had performed over 8.5 million steps across nearly 5 decades, and continued working even after its supplemental heater was turned off and its temperature plunged to negative 62 degrees Celsius. The engineering is remarkable, but the power to run the full instrument is simply no longer available. That leaves two science instruments on the most distant human-made object in existence, the magnetometer and the plasma wave subsystem, 2 ears pressed against the darkness. Everything else has been silenced. It is worth understanding what those two ears are actually hearing, because the data they collect is not merely interesting, it is unprecedented. No other instrument in human history has directly measured the environment between stars. Everything we knew about interstellar space before Voyager 1 arrived there was inferred, indirect, modelled from observations made at great distances. Voyager 1 is the first and still the only contact probe humanity has placed in the medium that fills the galaxy between solar systems. The magnetometer measures the interstellar magnetic field, the faint web of magnetism that permeates the space between stars. This field is generated by the collective motion of charged particles throughout the galaxy, shaped by supernova explosions, stellar winds, and the rotation of the Milky Way itself. Before Voyager 1 crossed the heliopause, scientists had theoretical predictions for the strength and direction of this field. Voyager 1's measurements surprised them. The magnetic field direction in the immediate interstellar medium turned out to be different from what most models predicted, tilted at an unexpected angle that forced revisions to our understanding of how the heliosphere interacts with its galactic surroundings. Every day, the magnetometer continues to operate. It refines our map of an environment that no Earth-based telescope can observe directly. The plasma wave subsystem listens to something even stranger. It detects oscillations in the plasma that fills interstellar space, vibrations in the thin soup of electrons and ions that exists between the stars. When this plasma vibrates, it produces waves at specific frequencies that depend on the density of the material. The plasma wave subsystem can convert these oscillations into audio frequencies that human ears can process. NASA has released recordings of these signals, and they are haunting, a low, steady hum punctuated by occasional bursts and whines. The sound of interstellar space itself, translated into something a human brain can register. It sounds alien because it is alien. No human ear was ever meant to hear the vibrations of plasma 17 billion miles from the sun. But the plasma wave subsystem hears them, and it sends them home, and for as long as that instrument operates, we can listen to the sound of the void between stars. What Voyager 1 has already discovered in that void has rewritten parts of astrophysics. Since crossing into interstellar space, the instruments have revealed that the medium between stars is far more textured and dynamic than anyone assumed. Rather than finding a uniform bath of thin particles, Voyager 1 has measured a changing environment, one whose properties shift as the spacecraft moves farther from the boundary it crossed in 2012. The density of the surrounding material is not constant. It varies with distance, suggesting the spacecraft is traversing a structured region whose features no Earth-based telescope could have mapped. Every additional astronomical unit of travel reveals new gradients, new variations, new evidence that interstellar space is not the featureless void that decades of indirect observation had led scientists to expect. No model fully predicted this gradient. It was a discovery made possible only because a machine was actually there, tasting the medium instead of studying it from 4 billion miles away through a telescope. Voyager 1 also detected unexpected pressure waves rippling through the interstellar plasma. In 2020 and 2021, the plasma wave subsystem registered a persistent, low-frequency hum that appeared to represent a nearly continuous background vibration in the local interstellar medium. Scientists had expected interstellar space to be quiet between major disturbances like solar storms or coronal mass ejections. Instead, Voyager 1 found that the plasma hums constantly, vibrating at a frequency that corresponds to the natural oscillation of the local medium. The space between stars is not silent. It rings, faintly and continuously, with a sound that no one knew existed until a 50-year-old spacecraft drifted into it and listened. Every day those two instruments remain powered. They extend a dataset that no other mission can replicate. No spacecraft currently in development is designed to reach interstellar space. No mission on any space agency's roadmap will arrive at the heliopause within the next several decades. When Voyager 1's magnetometer and plasma wave subsystem finally go dark, the window closes. The direct measurement of interstellar space ends, and it may not reopen for a century or more. What is dying is not just a spacecraft. It is a sensory connection to a place humanity has reached exactly once, and may not reach again within the lifetime of anyone alive today. And yet, the team at JPL has not given up. They are preparing a maneuver they have nicknamed the Big Bang. The concept is both elegant and desperate. Rather than continuing to shut down instruments one at a time in a slow retreat, the Big Bang involves swapping out a group of powered devices all at once, replacing certain power-hungry components with lower power alternatives in a single coordinated move. The goal is to create a new sustainable power equilibrium, a configuration where the spacecraft can stay warm enough to avoid freezing its fuel lines while still running at least some science instruments. Freezing is the silent killer. Voyager 1's thrusters use hydrazine fuel, and if the fuel lines freeze, the spacecraft can no longer orient its antenna toward Earth. Communication ends instantly and irreversibly. Every heater that gets turned off to save power brings the fuel lines closer to that freezing threshold. The Big Bang tries to thread the needle by finding a combination of shutdowns and replacements that maximizes both warmth and science. The risk is that threading the needle means moving the needle. When you change one system on a spacecraft, you can monitor the consequences and respond if something goes wrong. When you change multiple systems simultaneously, the consequences interact. A replacement component might draw slightly more power than predicted. A heater shutdown might drop a fuel line temperature faster than thermal models anticipated. A software change might conflict with an aging memory chip that has not been tested under the new power configuration. Any one of these problems in isolation would be manageable. Several occurring at once could trigger a cascading failure, a chain of automated fault protection responses that shuts the spacecraft down into a minimal safe mode. Recovering from safe mode at Voyager 1's distance is a process measured in weeks, not hours, because every diagnostic question takes 2 days to ask and answer. And each week spent in safe mode is a week without science, a week of fuel lines sitting at dangerously low temperatures, a week where a second anomaly could push the spacecraft beyond recovery. The maneuver earned its nickname not because it creates something new, but because if it fails, the consequences are immediate, simultaneous, and potentially irreversible. The plan is to test it on Voyager 2 first. Voyager 2 has slightly more power available and is closer to Earth, making it a safer test subject. Tests were scheduled for May and June of 2026. If they work, the same procedure will be attempted on Voyager 1 no earlier than July. If the Big Bang succeeds, there is even a possibility that the low-energy charged particles experiment could be switched back on. A resurrection, a second life for an instrument that has already outlived every engineering expectation placed on it. But even the most optimistic projections only extend the mission by years, not decades. The plutonium does not care about human ingenuity. It decays at the rate physics demands. Every year, 4 more watts vanish. No engineering trick can change the half-life of an isotope. Sometime in the late 2020s or early 2030s, the available power will drop below the threshold needed to operate any science instrument at all. The spacecraft will no longer collect data. Sometime after that, perhaps by the mid-2030s, the power will drop below the level needed to maintain a radio link with Earth. The 23-watt transmitter, already whispering across 15 billion miles of void, will fall silent. The Deep Space Network, NASA's array of massive radio dishes spread across California, Spain, and Australia, will listen and hear nothing. The last signal will arrive at Earth traveling at the speed of light, carrying information about conditions in interstellar space that existed a full day earlier, and then there will be silence. There is a strange and specific detail about that silence that makes it even more haunting. Only one antenna on Earth can still send commands to Voyager 1. It is DSS-43, a 230-foot wide radio dish located in Canberra, Australia. No other antenna in the Deep Space Network has the right combination of power, frequency, and pointing capability to reach the spacecraft. If that single dish goes offline for any reason, maintenance, equipment failure, a scheduling conflict with another mission, NASA loses the ability to speak to Voyager 1 entirely. The other antennas in California and Spain can still listen. They can still receive the spacecraft's faint transmissions, but they cannot send a single word back. The connection becomes one-directional, a voice calling from the darkness that no one on Earth can answer. This is the reality of Voyager 1 in 2026. A spacecraft with 2 working instruments, a power supply that loses 4 watts every year, a radio transmitter running on 23 watts, and a single antenna on one continent on Earth that can still reach it. The margins are razor thin. Every decision matters. Every watt counts. The engineering team is performing what amounts to end-of-life care on a machine that has outlived its original designers, its original mission, and every reasonable expectation anyone ever had for it. But here is the part that most people miss. Here is the part that turns this story from a slow engineering farewell into something much stranger and much larger. Voyager 1 has no brakes. There is no engine that can slow it down. There is no reverse thruster. There is no mechanism on board, none ever built into it, that can reduce its velocity through space. The small thrusters it carries are attitude control jets, designed only to rotate the spacecraft and keep its antenna pointed at Earth. They do not change its speed. They do not alter its trajectory in any meaningful way. Voyager 1 is moving at approximately 17 kilometers per second relative to the Sun. That is roughly 38,000 miles per hour, or about 3.5 astronomical units per year. It has been travelling at essentially this speed since its flyby of Saturn in November of 1980. The gravity assists from Jupiter and Saturn gave it enough velocity to escape the Sun's gravitational pull entirely. It is on a hyperbolic trajectory. It will never fall back. It will never return. It will never slow to a stop. This velocity requires no power. It requires no fuel. It is simply the motion of an object that was flung hard enough to escape the gravity of its home star. Newton's first law governs what happens next. An object in motion stays in motion unless acted upon by an external force. In interstellar space, there are almost no external forces, no atmospheric drag, no friction, no significant gravitational pull from any nearby object. The spacecraft will continue at roughly 17 kilometers per second, effectively forever. This is the distinction that changes everything. When people hear that Voyager 1 is dying, they imagine the spacecraft powering down and drifting to a halt, like a car running out of fuel on a highway. That is not what happens. The power system governs the instruments, the computers, the radio, the heaters. It governs the spacecraft's ability to think, to sense, to communicate, but it does not govern its motion. Voyager 1's motion is a consequence of physics, not engineering. The engines stopped firing decades ago. The speed is a gift from Jupiter and Saturn, from the gravitational slingshots that set it on its course. That gift does not expire. That gift does not decay. That gift does not lose 4 watts per year. When the power finally dies, the instruments will go dark. The computers will shut down, the transmitter will stop, the heaters will fail, and the spacecraft's internal temperature will eventually equalize with the surrounding interstellar medium, dropping toward a few degrees above absolute zero. The hydrazine will freeze, the electronics will become inert, the golden record, that gold-plated copper disc carrying sounds and images of Earth, will sit in its aluminum cover, undisturbed, and the spacecraft will keep moving at 17 kilometers per second, in the same direction it has been heading since 1980, 35 degrees above the plane of the planets, aimed toward the constellation Ophiuchus. Through interstellar space so empty that the chances of hitting anything are almost zero, silent, dark, cold, but not still, never still, moving at a speed that would carry it from New York to Los Angeles in about 4 minutes. Moving through a medium so sparse that a cubic centimeter of it, a volume smaller than a sugar cube, contains on average less than a single atom. Moving without purpose, without awareness, without anyone watching. This is what it means for Voyager 1 to die. The mission ends, the communication ends, the science ends, but the journey does not. The journey continues on a timescale that dwarfs the entire history of human civilization. The spacecraft will cross distances so vast that the concept of where begins to lose meaning. It will pass through regions of space where no human telescope can track it, where no instrument on Earth can detect it, where the only evidence it ever existed is the mathematics of its trajectory, calculated decades ago by engineers who are themselves now gone. The death of Voyager 1 is not a moment, it is a transition, a crossing from one kind of existence into another, from a spacecraft that talks to a spacecraft that drifts, from an explorer to an artifact, from a mission to a monument. And the unsettling part, the part that will haunt the rest of this story, is that the drifting phase will last incomparably longer than the talking phase. The entire era of active communication, from launch in 1977 to the last faint whisper sometime in the 2030s, spans roughly 60 years. The era of silent drifting that follows could span millions, billions, a length of time so enormous that 60 years of active mission vanishes inside it like a single heartbeat in a human lifetime. Voyager 1 is not approaching an ending. It is approaching a beginning. The beginning of the longest journey any human-made object will ever take. A journey with no destination, no audience, and no return. A journey that starts the moment the last signal fades and continues into a future so remote that the stars themselves will have rearranged. And somewhere along that unimaginably long road, there is one more named place. One final landmark that scientists can still point to and say, there, that is where it is headed. A small red star, dim and cold, racing toward our solar system from the direction of a constellation most people have never heard of. That star is the last stop before the silence becomes total and the journey becomes truly infinite. But to understand why that star matters, we first need to understand what happens the moment Voyager 1 stops talking, because the gap between the last signal and the last named place is not measured in years. It is measured in millennia, and what fills that gap is something far stranger than silence. The conversation between Earth and Voyager 1 is the longest phone call in human history. It has been going on, with interruptions, for nearly 49 years. It crosses more than 15 billion miles of vacuum. It travels at the speed of light, the absolute fastest anything can move in this universe, and it still takes an entire day to arrive. This is not a metaphor. If you spoke a word to Voyager 1 right now, that word, encoded as a radio signal and fired from the largest transmitting antenna on the planet, would not reach the spacecraft until tomorrow. The spacecraft's reply, assuming it could answer, would not arrive back at Earth until the day after. A single exchange of information requires 2 full days, a question and an answer separated by 46 hours of silence, during which the signal crosses a distance so vast that the human mind quietly gives up trying to picture it. And yet the conversation continues. Every day, data trickles in. Not much. The stream is thin, measured in bits per second rather than the megabits per second we expect from our home internet connections. Voyager 1 currently transmits at approximately 160 bits per second. For comparison, a single high-resolution photograph from a modern smartphone contains roughly 30 million bits. At Voyager 1's data rate, transmitting that photograph would take over 2 days. The bandwidth is agonizing by modern standards, but every bit that arrives has traveled farther than any piece of information in human history. Every bit is a whisper from the edge of the known. The machinery that makes this conversation possible is as remarkable as the spacecraft itself. On the Earth side, the conversation depends on the Deep Space Network, a collection of 3 radio antenna complexes spaced roughly 120 degrees apart around the globe. One sits near Goldstone, California, in the Mojave Desert. Another is near Madrid, Spain. The third is near Canberra, Australia. The spacing is deliberate. As the Earth rotates, at least one complex always has line of sight to any given point in deep space. Together, they provide continuous coverage. The sun never sets on the Deep Space Network. Each complex contains multiple antenna dishes of varying sizes. The workhorses are the massive 70-meter dishes, roughly 230 feet across, the largest steerable radio antennas ever built. These giants can detect signals so faint they make a whisper in a hurricane sound deafening by comparison. The signal arriving from Voyager 1 carries approximately 23 watts of transmitting power at the source. By the time that signal reaches Earth, after spreading across 15 billion miles of space, the received power has been calculated at roughly 20 billion times weaker than the power needed to run a digital wristwatch. Detecting it requires antennas the size of football fields, cryogenically cooled receivers, and signal processing techniques refined over decades. The fact that this works at all is one of the quiet engineering miracles of the 20th century. The miracle is even more improbable than it sounds. Voyager 1's signal does not arrive at Earth as a clean, clear tone that the antenna simply amplifies. It arrives buried in noise. The cosmic background, the faint hiss of the Big Bang, the radio emissions of the Sun, the electrical noise generated by Earth's own atmosphere, and the antenna's own electronics, all of these sources produce signals that are individually stronger than the whisper arriving from Voyager 1. The spacecraft's signal is below the noise floor. It is quieter than the static. If you pointed the antenna at the sky and simply listened, you would not hear Voyager 1 at all. You would hear noise. Extracting the signal requires a technique that borders on mathematical alchemy. Engineers know the exact frequency at which Voyager 1 transmits. They know the precise modulation pattern the spacecraft uses to encode its data. They use this knowledge to build a template, a mathematical model of what the signal should look like. Then they compare the incoming noise to that template, searching for correlations between the random static and the expected pattern. Over time, the random noise averages out. The signal, because it repeats consistently in the same pattern, does not. It accumulates. Bit by bit, the signal emerges from the noise like a face slowly appearing in a cloud of static. The process requires hours of continuous reception for even small amounts of data. It requires exquisite frequency stability, with the receivers cooled to a few degrees above absolute zero to minimize thermal noise in the electronics. It requires atomic clocks to maintain timing precision measured in billionths of a second, and it requires patience. A patience calibrated not in human minutes but in light hours and orbital mechanics. The received signal power, after crossing more than 15 billion miles, has been estimated at roughly 0.0000000000000000001 watts. Written in scientific notation, that is approximately 10 to the negative 16th watts. To put this in perspective, the energy delivered to the antenna by Voyager 1's signal over the course of an entire year is less than the energy required to lift a single grain of rice by 1 millimeter. The antenna is detecting something that carries less energy than a whisper carries sound pressure, less energy than a snowflake exerts when it lands on your sleeve. And from this vanishingly faint trace, engineers extract data about the magnetic field strength and plasma density of interstellar space more than 15 billion miles away. The thread connecting Earth to Voyager 1 is not just thin, it is thinner than anything you have ever held. And it holds, for now, because human beings figured out how to hear something quieter than silence. Operating a spacecraft under these conditions requires a discipline that has no parallel in any other field of engineering. The Voyager team cannot fly the spacecraft the way a pilot flies an aircraft, reacting to conditions in real time, adjusting course as problems appear. The 2-day round-trip communication delay makes real-time control impossible. Instead, the team operates through pre-scripted command sequences, carefully constructed packages of instructions that are written, tested, reviewed, and rehearsed before they are ever transmitted. Every command sequence is first run on a ground-based software simulator at JPL, a digital replica of Voyager 1's onboard computers that mimics the spacecraft's responses as closely as decades-old documentation allows. Engineers watch the simulator execute each instruction, looking for conflicts, unexpected power draws, thermal consequences, anything that could cause a problem. 15 billion miles away where no one can intervene in less than 46 hours. The sequences must anticipate failure. Because the team cannot react to a crisis as it unfolds, they build contingency logic into the command batches themselves. If this heater fails, switch to that backup. If this power threshold is crossed, shut down this instrument before the fault protection system does it uncontrollably. If the spacecraft enters safe mode, execute this recovery routine automatically. It is medicine practiced at a distance no doctor has ever faced, writing standing orders for a patient you cannot visit, cannot examine, cannot touch, and whose vital signs arrive a full day after they were measured. The engineers do not manage the spacecraft. They prepare it to manage itself, and then they wait, watching data arrive from yesterday, hoping the instructions they sent the day before that did what they were supposed to do. The team itself has shrunk to a handful of people. At the height of the planetary encounters in the late 1970s and early 1980s, hundreds of scientists and engineers worked on the Voyager missions. Today, the full-time Voyager team at JPL numbers fewer than a dozen. These are people who have dedicated years, in some cases decades, of their careers to keeping two aging spacecraft alive at the edge of the solar system. They know every subsystem, every quirk, every workaround that has accumulated over nearly 5 decades of continuous operation. Some of them were not born when the spacecraft launched. They inherited the mission from engineers who have since retired or died, learning the spacecraft's personality the way a new mechanic learns an old car, through institutional memory, handwritten notes, and hard-won experience. When Voyager 1 finally goes silent, it will not be a machine that dies, it will be a relationship. A daily practice of care and attention maintained across 15 billion miles that simply runs out of power to sustain. But there is a catch. While all 3 complexes can receive Voyager 1's signal, only one antenna on the entire planet can transmit commands back to it. That antenna is DSS-43, the 70-meter dish in Canberra. The reason is technical. Voyager 1's receiver operates on a specific frequency band, and DSS-43 is the only dish in the network equipped with a transmitter powerful enough on that band to reach the spacecraft at its current distance. The Goldstone dish, DSS-14, and the Madrid dish, DSS-63, can listen. They cannot speak. If DSS-43 goes down, Earth can still hear Voyager 1, but it cannot send a single instruction. The spacecraft becomes unreachable. It follows its last set of commands until those commands expire or something goes wrong. This already happened. From May 2025 through February 2026, DSS-43 went offline for major structural and electronic upgrades, with only brief windows of availability in August and December. For most of that period, the Voyager team at JPL could do nothing but listen. They received data. They monitored the spacecraft's health, but they could not intervene. If something had gone wrong during those months, if a heater had failed, if a thruster had misfired, if the power had dipped below a critical threshold, they would have heard the problem unfolding across 15 billion miles and been completely powerless to help. Voyager 1 spent those months the way it will eventually spend the rest of eternity. Alone, unreachable, following its own trajectory through the dark. That preview of silence is about to become a milestone. In November of 2026, Voyager 1 will become the first human-made object to reach a distance of 1 light day from Earth. 1 light day. 24 hours for a signal to travel from our planet to the spacecraft. The moment is more symbolic than scientific, a round number on an ever-growing odometer, but it carries emotional weight that is hard to dismiss. When Voyager 1 crosses that threshold, it will mean that a full Earth day elapses between the moment a message leaves our world and the moment it arrives at the spacecraft. A command sent on a Monday morning will not be received until Tuesday morning, and by the time the reply crawls back, the spacecraft will have moved farther still, widening the gap with every passing second. 1 light day is equivalent to roughly 16 billion miles, or about 26 billion kilometers. That distance is already so large that it strains every familiar reference point. If you laid more than 18,000 copies of the Sun side by side, edge to edge, the line of stars would only just stretch across that distance. The sheer emptiness between Earth and Voyager 1 contains nothing of consequence. No planets, no moons, no asteroids. Occasional wisps of interstellar hydrogen so thin that a thimble-sized sample would contain fewer atoms than you could count on one hand. Voyager 1 is out there in a void so complete that the word alone does not begin to capture it. And it will only get worse. The spacecraft moves farther from Earth every second of every day, adding roughly 17 kilometers per second to the gap. That means every year, the one-way signal time grows by roughly half an hour. By 2030, the light travel time will exceed 25 hours. By 2035, it could approach 28 hours. Each additional hour represents millions of additional miles of empty space between the spacecraft and the only planet that knows it exists. This is the slow-motion goodbye, not a dramatic cutoff, not a sudden loss of signal, a gradual stretching of the thread that connects the spacecraft to home. The data rate drops as the signal weakens. The power budget shrinks as the plutonium decays. The instruments go dark one by one. The conversations grow longer and quieter, and at some point in the mid-2030s, the thread snaps. Not because anyone cuts it, because the whisper from 15 or 16 billion miles away finally fades below the threshold of detection. The Deep Space Network will listen, and for the first time in nearly 6 decades, it will hear nothing. That moment will not appear on the spacecraft's instruments, because the spacecraft's instruments will already be dead. It will not register in any sensor aboard Voyager 1, because no sensor will be drawing power. The moment the line goes dead is entirely an Earthside event. It is us who lose contact. It is us who stop hearing. The spacecraft notices nothing. It experiences nothing. It simply continues doing what it has been doing since 1980, moving. Here is where the story makes a turn that most people do not expect. When Voyager 1 goes silent, nothing about its physical trajectory changes, not its speed, not its direction, not its position relative to the stars. The loss of power affects the spacecraft's ability to function as a machine. It does not affect the spacecraft's existence as an object, and objects in motion stay in motion. Voyager 1 is currently heading 35 degrees above the ecliptic plane, the flat disk in which the planets orbit the Sun. Its trajectory carries it in the general direction of the constellation Ophiuchus, though it will not pass particularly close to any star in that constellation. The direction was not chosen for any interstellar destination. It was a consequence of the Saturn flyby in November 1980. When Voyager 1 swung past Saturn and its moon Titan, the gravitational slingshot flung it upward and outward relative to the plane of the solar system. The angle was determined by orbital mechanics, by the positions of Jupiter and Saturn at the time of the flybys, by the trajectory needed to get close to Titan. Nobody pointed Voyager 1 at a star. The stars it will eventually approach are accidents of geometry, consequences of a path chosen for planetary science nearly half a century ago. The speed is equally fixed. 17 kilometers per second, the same velocity it has carried since Saturn. Fast by human standards, painfully slow by interstellar standards. At this speed, Voyager 1 would need about 73,000 years to cross the distance to the nearest star system, Alpha Centauri, if it were heading in that direction. It is not. The nearest star on its actual path is a dim red dwarf that most people have never heard of, and even that encounter is roughly 40,000 years in the future. 40,000 years. Let that settle for a moment. 40,000 years ago, Neanderthals still shared Europe with early modern humans. The cave paintings at Lascaux did not yet exist. Agriculture was 25,000 years away. Writing was 35,000 years away. The entire recorded history of human civilization, every empire, every war, every invention, every book, every song, fits inside less than a quarter of the time that will pass before Voyager 1 reaches its next meaningful waypoint. And during every one of those 40,000 years, the spacecraft will be silent, dark, cold, carrying a golden record that no one is playing, aimed at a star that no one on Earth can see with the naked eye. But before Voyager 1 reaches that star, it must cross a region that is itself barely understood. The spacecraft is currently in interstellar space, meaning it has passed beyond the heliosphere, the bubble of charged particles and magnetic fields generated by the Sun. Voyager 1 crossed the heliopause, the outer boundary of the heliosphere, on August 25, 2012, becoming the first human-made object to enter the space between stars. That crossing was confirmed by a sudden spike in the density of plasma around the spacecraft and a corresponding drop in solar origin particles. The Sun's influence had ended. Voyager 1 was in somebody else's ocean. That crossing was itself one of the great scientific detective stories of the 21st century. Voyager 1 did not pass through a clean boundary. With a welcome sign, the heliopause turned out to be messy, gradual, and deeply confusing. For years before the official crossing date, the spacecraft sent back contradictory signals. Solar origin particles would drop, then rise again. The magnetic field direction would shift, then shift back. Scientists debated fiercely whether Voyager 1 had actually crossed the heliopause or was passing through a strange transitional region that no model had predicted. The definitive evidence came not from the magnetic field data, but from the plasma measurements. In April 2013, scientists analysing plasma wave subsystem data realised that a coronal mass ejection from the Sun, a massive burst of solar plasma launched in March 2012, had reached Voyager 1's position and caused the surrounding interstellar plasma to vibrate. The frequency of that vibration revealed the plasma density, and the density was roughly 40 times higher than what would be expected inside the heliosphere. The spacecraft was immersed in interstellar plasma. It had crossed the boundary. Working backward from the plasma data, scientists pinpointed the crossing date as August 25, 2012. Voyager 1 had entered interstellar space more than a year before anyone on Earth was certain it had happened. The announcement, when it came in September 2013, made headlines around the world, but the crossing itself had occurred in silence. No alarm sounded on the spacecraft. No instrument registered a dramatic threshold. The most significant boundary crossing in the history of space exploration happened without ceremony, confirmed only by detective work performed across a distance of more than 11 billion miles, more than a year after the fact. What made the crossing scientifically extraordinary was what came next. The interstellar medium that Voyager 1 entered was not the uniform, predictable environment that textbook models had described. The plasma density was higher than expected. The magnetic field was oriented differently than predicted. And the boundary itself, rather than being a sharp wall, turned out to be a complex layered region where solar and interstellar material intermixed in patterns that no simulation had fully anticipated. Voyager 1 did not just confirm that interstellar space exists. It revealed that interstellar space is stranger and more structured than anyone had assumed. Every year of continued operation since that crossing has added detail to a picture that only one instrument in human history can paint. From the only vantage point that matters, the vantage point of being there. But interstellar space is not the same as being outside the solar system. This is a distinction that surprises many people. The Sun's gravitational reach extends far beyond the heliosphere. Objects orbiting the Sun exist at distances of 50,000 astronomical units and beyond, in a vast, cold, spherical shell of icy bodies called the Oort Cloud. The Oort Cloud is the outermost structure of the solar system, a reservoir of trillions of frozen objects left over from the formation of the planets 4.5 billion years ago. Long-period comets, the ones that take thousands or millions of years to complete a single orbit, originate here. The inner edge of the Oort Cloud begins at roughly 1,000 to 2,000 astronomical units from the Sun. The outer edge may extend to 100,000 astronomical units, more than 1.5 light years. Voyager 1, at approximately 170 astronomical units, has barely begun this crossing. At its current speed of 3.5 astronomical units per year, it will take roughly 300 years just to reach the inner edge of the Oort Cloud. 300 years from now, the spacecraft will enter a region of space filled with ancient ice, and it will have been silent for more than 270 of those years. No instrument will detect the icy bodies drifting past. No camera will photograph them. The spacecraft will thread its way through the Oort Cloud the way a bullet passes through fog, too small and too fast to interact with anything, too dead to notice if it did. The Oort Cloud deserves a moment of its own, because Voyager 1 will spend more time inside it than it spent doing everything else combined. 30,000 years. That is longer than the span from the last ice age to the present day. And during every one of those 30,000 years, the spacecraft will be drifting through a structure that no human telescope has ever directly observed. The Oort Cloud is hypothetical in the strictest sense. No one has ever photographed an Oort Cloud object in situ. No instrument has directly detected the cloud's inner or outer boundary. Its existence is inferred entirely from the behavior of long-period comets, the ones that take thousands or millions of years to complete a single orbit around the Sun. These comets arrive from every direction, not just from the flat plane where the planets orbit, suggesting they originate from a spherical shell rather than a disk. Their orbital characteristics imply a vast reservoir of icy bodies at distances ranging from roughly 1,000 to 100,000 astronomical units from the Sun. The Dutch astronomer Jan Oort first proposed this reservoir in 1950, and the evidence has only strengthened since. The objects in the Oort Cloud are believed to be remnants of the solar system's formation, icy planetesimals that were gravitationally scattered outward, by the giant planets during the chaotic early era when Jupiter and Saturn were still migrating through the solar system. These bodies were flung to enormous distances but remained gravitationally bound to the Sun, settling into a vast, diffuse shell that marks the outermost frontier of our star's gravitational domain. Estimates of the total number of objects vary enormously, from several hundred billion to perhaps 2 trillion, with a combined mass that may be several times the mass of Earth. But spread across a sphere 100,000 astronomical units in radius, this material is astonishingly sparse. The average distance between Oort Cloud objects is estimated at tens of millions of kilometers, possibly hundreds of millions. It is a cloud in name only. In practice, it is a near-perfect vacuum, occasionally punctuated by frozen objects no larger than mountains, drifting in orbits so slow that a single trip around the Sun takes millions of years. The objects themselves are ancient, unaltered, preserved in the deep freeze of the outer solar system for 4.5 billion years. They are made of water ice, frozen methane, ammonia, and carbon dioxide, mixed with silicate dust and organic compounds. They are time capsules from an era when the solar system was still assembling itself, before the planets had reached their current orbits, before the Earth had cooled enough for liquid water, before the moon-forming impact had reshaped our world. If a spacecraft could visit one and analyze its composition, it would be studying material that predates every rock on Earth's surface by billions of years. Voyager 1 will pass among these objects without detecting them, without touching them, without altering their ancient orbits by even a fraction of a millimeter. The spacecraft will be dead. The objects will be undisturbed. 2 relics from 2 different eras of the solar system's history, sharing the same dark, cold, silent space, unaware of each other's existence. Crossing the full extent of the Oort Cloud will take approximately 30,000 years. 30,000 years of drifting through a shell of frozen debris so sparsely distributed that the odds of Voyager 1 actually striking an Oort Cloud object are essentially zero. The average distance between objects in the Oort Cloud is estimated at tens of millions of kilometers. Voyager 1 is less than 4 meters across. Threading a needle does not begin to describe the improbability of a collision. The spacecraft will pass through the entire cloud without touching a single grain of ice, and then it will be out. Truly out. Free of the Sun's gravitational domain for the first time since it was launched from a planet that orbits that star. At that point, roughly 30,000 years from now, Voyager 1 will no longer belong to the solar system in any meaningful sense. It will be a free drifting object in the galaxy, subject only to the combined gravitational pull of every star and mass concentration in the Milky Way. It will have been silent for approximately 29,940 years, and it will still be moving at 17 kilometers per second. This is the timeline that reframes everything about what it means for Voyager 1 to die. Those 60 years of active life, the entire span from launch to last signal, would fit inside the Oort Cloud crossing 500 times over. 30,000 years of silence for every 60 years of speech. The talking phase is not the main event. It is the opening syllable of a sentence that takes millennia to finish. The talking phase is a rounding error, a flash, a single breath before a silence that stretches across an interval 500 times longer. And yet 30,000 years is still not the timescale that matters most to this story, because the Oort Cloud is merely the porch. Beyond it lies the interstellar medium, the true space between stars, and in that space, Voyager 1 has a date, not a collision, not a capture, a passage, a fleeting encounter with a dim red star that will, for a brief window of cosmic time, become the closest star to the spacecraft, closer than the Sun, closer than any other point of light in the galaxy. That encounter, roughly 40,000 years from now, represents the last place on Voyager 1's trajectory that human scientists can currently name with any confidence. The last pin on the map, the last entry in the logbook. Beyond it, the uncertainties in stellar motion and galactic dynamics grow too large to make specific predictions. The spacecraft will continue moving, certainly. It will pass other stars at various distances over the following millions and billions of years, but we cannot say which stars, or when, or how close. The trajectory predictions dissolve into probability clouds and statistical averages. the named journey ends. What makes this especially haunting is the nature of the encounter itself. Voyager 1 will not enter orbit around this star. It will not be captured by its gravity. It will not slow down. At 17 kilometers per second, the spacecraft will streak past at a distance of roughly 1.6 light-years, which is about 9.5 trillion miles. That is closer than the current gap between the Sun and the nearest star to our solar system, Proxima Centauri, which sits 4.2 light-years away. But 1.6 light-years is still an almost unimaginable distance. If the star were scaled to the size of a marble, Voyager 1 at its closest approach would be passing by at a distance of roughly 400 miles. The encounter, in any human sense of the word, is not an encounter at all. It is two objects existing in the same general region of galactic space, unaware of each other, separated by a gulf that light itself needs almost 2 years to cross. Voyager 1 will not detect the star. It will not photograph it. It will not feel its warmth. By the time this passage occurs, the spacecraft will have been dead for approximately 39,940 years. Its electronics will have degraded. Its internal wiring may have been slowly damaged by cosmic ray bombardment over millennia. The only part of the spacecraft likely to remain structurally intact on that timescale is the golden record itself, a disk of gold-plated copper designed to resist the erosion of interstellar space for hundreds of millions of years. The record will still exist. The music encoded on it, Chuck Berry and Beethoven and Blind Willie Johnson, will still be etched into its grooves, but no arm will lower onto its surface. No speaker will play its contents. The record will pass by a star in perfect silence, carrying greetings in 55 languages to an audience of 0. This is the moment the story pivots. Because the question we started with, the final place Voyager 1 will ever reach before it dies, turns out to be the wrong question. Or rather, it is a question whose answer reveals something deeply uncomfortable about how we think about endings. Voyager 1 does not reach a final place and then die. It dies first. It dies decades before it reaches anything. The mission ends in the 2030s. The Oort Cloud transit begins 300 years later. And 5 more, the stellar encounter occurs 40,000 years after that. The spacecraft is dead for almost the entire journey. The final place is not a destination that Voyager 1 arrives at while still alive. It is a landmark that the corpse drifts past, tens of thousands of years after the funeral, and what comes after that landmark is not an ending either. It is a continuation so long and so silent that the 40,000 years preceding it start to look brief. Because after the last named star, Voyager 1 does not stop. There is nowhere for it to stop. There is nothing to stop it. It drifts onward into a galaxy that will slowly rearrange itself around a tiny, frozen, silent piece of human engineering. And the timescales that govern that onward drift are no longer measured in thousands of years. They are measured in millions, in billions. In spans of time that make the entire existence of the human species look like a momentary flicker. That is where the real story waits. Not in the death, not in the silence, but in what comes after both. There is a star you have almost certainly never heard of. It does not appear in any mythology. It carries no ancient name, no civilization has ever navigated by it. No poet has written about it. It is invisible to the naked eye, too dim and too distant for anyone standing on Earth to see without a telescope. Its catalogue designation is Gliese, 445, sometimes also listed as AC plus 79, 3888. It is a red dwarf, a class of star so small and so cool that it produces less than 1% of the Sun's luminosity. If you replace the Sun with Gliese, 445, Earth would freeze solid within weeks. The oceans would turn to ice. The atmosphere would begin condensing into frost on the ground. It is a star that barely qualifies as a star, burning its hydrogen so slowly that it will outlive the Sun by trillions of years, but producing so little light that you would never notice it. Right now, Gliese, 445 is approximately 17 light-years from Earth. That places it in the constellation Camer-Lopar-Dalis, the Giraffe, a faint and sprawling constellation in the northern sky that most amateur astronomers would struggle to point out. 17 light-years is close by galactic standards. There are only a few hundred stars within that radius of the Sun. But 17 light-years is still roughly 100 trillion miles. Even at the speed of light, you would need 17 years to get there. At Voyager 1's speed of 17 kilometers per second, you would need about 300,000 years. So why does this unremarkable, invisible, nearly forgotten star matter to the story of Voyager 1? Because it is moving, fast, and it is moving toward us. Gliese, 445, is racing toward the Sun at approximately 119 kilometers per second. That is nearly 7 times faster than Voyager 1 itself is traveling. While the spacecraft slowly crawls outward from the solar system at 17 kilometers per second, this dim red dwarf is barreling inward at a speed that will dramatically close the gap between them. The encounter between Voyager 1 and Gliese 445 is less about the spacecraft reaching the star and more about the star coming to the spacecraft. It is like throwing a baseball into an open field while a truck drives toward it from the other direction. The ball is moving, yes, but the truck is doing most of the work. Over the next 40,000 years, the geometry reshapes itself. Gliese, 445, currently 17 light-years away, will close to within roughly 3.5 light-years of the Sun. At that distance, it will be closer to us than Proxima Centauri is today. Meanwhile, Voyager 1 will have travelled outward to a distance of roughly 1.6 light-years from the star's closest approach point. The spacecraft and the star will pass each other at this distance, approximately 1.6 light-years apart, around the year 40,272 AD. Some calculations place the encounter slightly later, around 44,000 years from now, depending on the precision of the stellar motion data used. But the order of magnitude is consistent across multiple studies. Roughly 40,000 years, roughly 1.6 light-years at closest approach. 1.6 light-years is about 9.4 trillion miles. In any human framework, this is not a close encounter. You could fit more than 1,000 copies of our entire planetary system, stretched from the Sun to Neptune and back, into that gap. But in the context of interstellar space, where the average distance between neighbouring stars is roughly 4 to 5 light-years, passing within 1.6 light-years is notable. It is closer than any star currently sits to our Sun. It is close enough that if Voyager 1 were still functioning, and if its instruments were somehow still operating after 40,000 years, it could theoretically detect the star's stellar wind, its magnetic field, and perhaps even the faint glow of its dim photosphere. Of course, none of this will happen. The spacecraft will have been dead for approximately 39,970 years by then, but the trajectory is real. The geometry is confirmed, the encounter will occur, observed by no one, recorded by nothing. This is the final place. The last named point on Voyager 1's journey that scientists can identify with reasonable confidence. Not because the spacecraft stops here, not because anything happens here, not because this star has any special significance in the grand catalogue of the cosmos, simply because it is the last object on Voyager 1's path whose future position can be predicted well enough to say, with scientific honesty, that the spacecraft will pass near it. Beyond Gliese, 445, the predictions fall apart, not because Voyager 1 stops moving, it does not, but because the uncertainties in stellar dynamics grow too large to make specific claims. Stars drift through the galaxy in complex paths governed by the combined gravity of billions of other stars, gas clouds, and dark matter concentrations. Predicting where a given star will be 40,000 years from now is difficult but feasible. Predicting where it will be 400,000 years from now is vastly harder. Predicting individual stellar positions millions of years into the future is essentially impossible with current data. The Milky Way is not a clockwork mechanism. It is a churning gravitational sea where stars jostle and drift and occasionally fling each other into new orbits. Over long enough timescales, the constellations themselves dissolve. Orion will not look like Orion in 100,000 years. The Big Dipper will warp into an unrecognizable shape. The sky rearranges itself constantly, too slowly for any human lifetime to notice, but fast enough to erase all familiar patterns over geological time. Voyager 1 will drift through this rearranging sky for millions of years after passing Gliese 445. It will come within various distances of other stars at various times, Statistical models suggest that a spacecraft moving through the galaxy at Voyager 1's speed will encounter a star within 1 parsec, roughly 3.3 light-years, approximately once every 50,000 years. Closer encounters, within 1/10 of a parsec, occur on average once every 5 million years. But these are averages. The specific stars, the specific distances, the specific timing, all of that is lost in the noise of galactic dynamics. We cannot name those future stars. We cannot point to them. We can only say that statistically, they will exist, somewhere, at some distance, at some time, that no human calendar will ever record. This is why Gliese 445 matters. It is the last entry in the logbook, the final pin on the map. After it, the map goes blank. Not because the territory ends, but because our ability to chart it does. It is worth pausing to understand what kind of star this is, because it says something about the nature of the encounter. Gliese 445 is an M-type main sequence red dwarf. It has roughly 1/4 the mass of the Sun. Its radius is about 1/4 of the Sun's radius. Its surface temperature is approximately 3,350 degrees Kelvin compared to the Sun's 5,778 degrees. It glows a deep, dull red, the kind of star that would barely register as a faint ember if you could see it up close. Its luminosity is roughly 8/1000ths of the Sun's output. It produces less light than a decent campfire produces heat, relatively speaking. Red dwarfs like Gliese 445 are the most common type of star in the galaxy. Roughly 70 to 75% of all stars in the Milky Way are red dwarfs. They are everywhere. They are also nearly invisible. Because they produce so little light, they are drastically underrepresented in our view of the night sky. Every star you have ever seen twinkling above you is either larger, hotter, or closer than the average red dwarf. The galaxy's most abundant residents are also its most hidden. Gliese 445 is a typical member of this silent majority, unremarkable in every measurable way except one. It happens to lie in the future path of the most distant object humanity has ever built. Whether Gliese 445 has planets is unknown. No exoplanets have been confirmed in orbit around it. That does not mean they do not exist. Our current detection methods are biased toward finding large planets around bright nearby stars. A dim red dwarf 17 light-years away with no known transiting companions could easily harbour a system of small rocky worlds that our instruments simply cannot see yet. If such planets exist, Voyager 1 will not visit them. A closest approach distance of 1.6 light-years places the spacecraft far outside any conceivable planetary system. Planetary orbits, even generous ones, extend to perhaps a few hundred astronomical units from their parent star. 1.6 light-years is roughly 100,000 astronomical units. The spacecraft will not graze Gliese 445's Oort Cloud equivalent, assuming such a structure exists around the star. It will not pass through any debris disk. It will not encounter any gravitational influence significant enough to alter its trajectory. The star is the destination in name only. In practice, Voyager 1 will sail through empty space 1.6 light-years from a dim red ember, and the ember will have no idea. This is the strange cruelty of interstellar distances. Even a close encounter, the closest that Voyager 1 will experience for tens of thousands of years, is so far apart that neither object has any physical effect on the other. The star does not pull the spacecraft. The spacecraft does not reflect the star's light in any detectable way. Two objects, each moving through the galaxy on their own trajectories, happen to pass within a distance that is cosmically small but physically enormous. And then they separate. Forever. Gliese 445 continues its journey toward and then past our solar system, eventually receding back into the depths of the galaxy. Voyager 1 continues outward, its trajectory unchanged, its course unaltered by the encounter. Voyager 1 is not the only human-made object on an interstellar trajectory. 4 other spacecraft are also leaving the solar system, each on a different heading, each aimed, by accident of orbital mechanics, at a different region of the galaxy. Voyager 2, launched 16 days before Voyager 1, in 1977, is heading south of the ecliptic plane toward the constellations Sagittarius and Pavo. In roughly 40,000 years, it will pass near the star Ross 248, another dim red dwarf, at a distance of roughly 1.7 light-years. Pioneer 10, launched in 1972, is heading toward the constellation Taurus. In approximately 2 million years, it will make a distant approach to Aldebaran, the bright orange giant that marks the eye of the bull. Pioneer 11, launched in 1973, is heading toward the constellation Aquila. Its distant future includes a passage near Lambda AK Willi, a young star roughly 3 times the mass of the Sun, but that encounter is also millions of years away. Each of these spacecraft carries some form of message. The Pioneer probes carry gold anodized aluminum plaques engraved with diagrams showing the position of our Sun relative to nearby pulsars, plus a line drawing of 2 human figures. The Voyager probes carry the golden records, those gold-plated copper discs containing 116 images, greetings in 55 languages, a 90-minute selection of music from around the world, and an audio essay of natural sounds, from thunder to birdsong to the cry of a humpback whale. These artifacts were designed with a specific kind of optimism. Carl Sagan, who chaired the committee that assembled the Golden Record's contents, understood that the probability of any of these spacecraft being found by another civilization was essentially zero. Space is too big. The spacecraft are too small. The distances are too vast. The timescales are too long. But Sagan argued that the act of creating the message was itself the point. The record was a statement about the kind of species we are, or at least the kind of species we aspire to be. A species that throws a bottle into the ocean knowing full well that no one will ever find it, but throws it anyway, because the act of reaching out matters more than the act of being received. The committee that assembled the Golden Record's contents had roughly 6 weeks to complete the task. 6 weeks to decide what Earth sounds like, what it looks like, what music defines an entire planet, what greeting could speak for a species that has never agreed on anything unanimously. The constraints were brutal. The record had a finite amount of groove space. Every minute of music added was a minute of something else that had to be cut. Every image included meant another image left behind. The committee was not selecting highlights. It was performing triage on the entire output of human civilization. The music selections reveal the agony of the choices. Bach made the cut 3 times. More than any other composer, his music judged to represent a peak of human artistic achievement that transcended cultural boundaries. Beethoven appeared twice, including the cavatina from his 13th string quartet, a piece that reportedly moved him to tears even at the mere thought of it, despite the fact that by the time he composed it, he was almost entirely deaf. A Javanese gamelan piece called Kinds of Flowers was included to represent the musical traditions of Southeast Asia. A Navajo night chant represented indigenous North America, or a Georgian chorus called Chakrulo represented polyphonic vocal music. And then there was Chuck Berry. His song Johnny Be Good was proposed as a representative of American rock and roll, and the suggestion drew immediate objections. One committee member argued that rock and roll was adolescent. Carl Sagan reportedly replied that there were a lot of adolescents on the planet. The song made the final cut. Somewhere beyond the heliosphere, the opening guitar riff of Johnny B. Good is etched into gold, travelling at 38,000 miles per hour toward a star that will not exist in its current position for another 40,000 years. The images were equally agonizing. 116 photographs and diagrams, selected to teach an alien intelligence what Earth is and who lives on it. A photograph of a woman nursing an infant was debated because of concerns about nudity, and ultimately included because the act of a mother feeding her child was judged to be among the most universal human experiences. A diagram of human DNA was included alongside images of traffic jams, supermarkets, and a page of text from a book. The committee was trying to compress the experience of being human into fewer than 120 frames. Every image was a judgment call about what matters most when you have one chance to explain yourself to the universe. But the most extraordinary item on the record is one that almost no one talks about. Among the audio contents is a recording of the brainwave patterns of Anne Druin, the creative director of the project. The recording was made using an electroencephalogram at a laboratory in New York, capturing an hour of Druyan's neural electrical activity as she thought about a prepared list of topics: the history of Earth, the nature of human civilization, what it feels like to fall in love. The recording was made on June 3rd, 1977, just 2 days after Druyan and Carl Sagan had privately confessed that they were in love with each other. Druyan later said that her thoughts during the recording were dominated by that new, overwhelming emotion. If the recording could ever be decoded, somewhere in those electrical patterns is the neurological signature of a woman experiencing one of the most profound feelings a human being can have, captured in analog waveform and launched into interstellar space, aboard a spacecraft that would outlive both her and the man she loved. The golden record does not just carry music and photographs. It carries the interior experience of being alive, etched in gold, aimed at no one, drifting toward a dim red star in the constellation of the Giraffe. Voyager 1's golden record will still be physically intact when the spacecraft passes Gliese 445. Gold-plated copper is remarkably durable. In the near vacuum of interstellar space, there is almost nothing to corrode it. No atmosphere, no liquid water, no biological agents. The primary threat to the record's integrity is cosmic ray bombardment. High-energy particles from distant supernovae and other galactic sources will slowly damage the disk's surface over millions of years, gradually eroding the grooves that carry the encoded sounds and images. Estimates suggest the record could remain at least partially readable for several 100 million years, possibly longer. The spacecraft's electronics will have degraded long before that. Circuit boards, wiring, magnetic tape, all of these are far more vulnerable to radiation damage and thermal cycling than a solid disk of metal. But the record endures. It was built to. This means that when Voyager 1 passes Gliese 445, it will be carrying a message that can still theoretically be decoded, attached to a spacecraft that can no longer decode it. The record player built into the spacecraft, a cartridge and stylus designed to be assembled by any sufficiently intelligent being who finds the probe, will still be present. The instructions etched onto the record's cover, explaining in symbolic language how to play it, will still be legible. But the spacecraft itself will be a husk, its computers silent, its transmitter dead, its instruments inert. The message survives. The messenger does not. There is a specific cruelty in this asymmetry that connects directly to the question posed by this story. What is the final place Voyager 1 will ever reach before it dies? The answer, we can now see, involves a redefinition of before. The spacecraft dies in the engineering sense in the 2030s, roughly 60 years after launch. Its last named waypoint, Gliese 445, lies 40,000 years in the future. The death comes first. The place comes after. The final place before it dies is actually the final place after it dies, viewed from the perspective of the trajectory rather than the timeline of the mission. It is the last meaningful landmark on a road that the spacecraft will travel as a corpse, and meaningful is doing a great deal of work in that sentence. 1.6 light-years is not a visit. It is not an arrival. It is not even a particularly close shave by interstellar standards. It is the nearest named star on a trajectory that extends into indefinite future time. We call it a destination because we need a word for the last identifiable point on a journey that has no end. But Gliese 445 does not mark an ending. It marks the boundary of human knowledge about where the spacecraft is going. Beyond this point, we lose the ability to narrate. The story does not conclude. Our capacity to tell it does. This distinction between the end of the story and the end of the journey is the core of what makes Voyager 1's fate so disquieting. We are accustomed to narratives that end when the protagonist reaches a destination or meets a final obstacle. The hero arrives, the ship docks, the explorer plants a flag. Voyager 1 offers no such closure. Its mission ends in a slow power failure. Its last named waypoint is a flyby so distant it barely qualifies as a proximity. And after that flyby, the journey continues for a span of time so vast that describing it requires language borrowed from geology and cosmology rather than human experience. Consider what fills the space between the mission's death and the Gliese 445 encounter. Roughly 40,000 years. During those 40,000 years, Voyager 1 spends most of the journey threading through the Oort Cloud, that vast shell of ancient ice surrounding the sun's gravitational domain, silent for virtually the entire crossing. Then come the remaining millennia of open interstellar space between the cloud's far edge and the star itself. But the odds of such a collision are vanishingly small. The Oort Cloud is not a minefield. It is a vast, sparse shell of frozen debris where the average spacing between objects is measured in tens of millions of kilometers. Voyager 1 is a needle-thin sliver of metal and wire, less than 4 meters wide, threading through a region where the nearest obstacle could be farther away than the distance from the Earth to the Moon. It will almost certainly pass through without incident, without contact, without consequence. Then come the remaining 10,000 years between the far edge of the Oort Cloud and the Gliese 445 encounter. 10,000 years of open interstellar space, far from the sun's gravitational influence, far from any detectable structure, moving through a medium so thin that it barely qualifies as matter. The interstellar medium in our region of the galaxy contains roughly 1 atom per cubic centimeter. Compare that to the air you are breathing right now, which contains approximately 25 quintillion molecules per cubic centimeter. Interstellar space is not empty in the absolute sense, but it is emptier than any vacuum humanity has ever created in a laboratory. Voyager 1 will spend 10,000 years gliding through this near-perfect nothingness, carrying a disk of music and greetings etched in gold, passing through a silence so profound that even the concept of sound loses meaning. When the spacecraft finally reaches its closest point to Gliese 445, approximately 40,000 years from now, the event will have no witnesses. No telescope on Earth will be tracking the spacecraft. No sensor aboard the probe will register the star's presence. The closest approach distance of 1.6 light-years means the star will be visible from the spacecraft's position as just another point of light, slightly brighter than the surrounding stars, slightly redder. If the spacecraft had eyes, it would see a faint ruby dot against an ocean of white points. It would not see planets. It would not see surface features. It would not see anything that distinguished this star from the thousands of other dim red dwarfs scattered through the galactic neighborhood. The encounter, such as it is, would be invisible to the naked eye even if someone were riding on the spacecraft's hull. And yet this is the best we can do. This is the strongest, most scientifically grounded future waypoint on Voyager 1's trajectory. Not a planet, not a star system, not even a true flyby. A passage through the general vicinity of a dim red dwarf at a distance of 9.5 trillion miles, 40,000 years after the spacecraft stopped functioning. This is the final place, the last pin in the map, the last entry in a logbook that will have been closed for almost 40 millennia. After Gliese 445, the predictions grow foggy. Statistical models can estimate the rate at which Voyager 1 will encounter other stars at various distances, roughly 1 star within 1 parsec every 50,000 years. Perhaps 1 star within half a parsec every 200,000 years. These are averages based on the density of stars in the solar neighborhood and the spacecraft's velocity. They tell us that Voyager 1 will continue to pass through regions of space where stars exist, but they cannot tell us which stars, or when exactly, or how close. The specificity vanishes. The narrative dissolves into statistics, and Voyager 1 drifts onward, a silent artifact in a galaxy full of stars it will never visit and worlds it will never see. What happens after that, the timescales that stretch beyond thousands into millions and billions, reveals the true scope of what humanity launched into the dark in 1977. The Gliese 445 encounter is not the end of Voyager 1's journey. It is merely the end of the chapter we can read. The book continues for unimaginable lengths beyond that last legible page, and the story it contains is one of silent, patient, incomprehensible endurance. That story waits at the end of this journey. Not a story of destinations, not a story of arrivals, a story of duration, of what it means to build something that will outlive not just its creators, not just their civilization, but possibly their star. After Gliese 445, the map goes blank, but the spacecraft does not care about maps. It does not know that we have run out of names for the places it is heading. It does not know that the last scientist who could have plotted its course has been dead for 39,000 years. It simply continues. 17 kilometers per second, the same speed it has maintained since a dead planet's gravity flung it outward in 1980. No acceleration, no deceleration, no deviation. A straight line through curved space-time, bending so gradually under the Milky Way's collective gravity that the deflection is imperceptible across merely human timescales. Voyager 1 does not travel in a straight line forever. Nothing in the galaxy does. It follows an orbit, just as the Sun does, around the center of the Milky Way. That orbit takes approximately 225 million years to complete. One full lap around the galaxy. One galactic year. Think about what that means for the spacecraft. The entire active mission, from launch to the last signal, fits inside 60 years. The encounter with Gliese, 445, occurs at 40,000 years. The crossing of the Oort Cloud takes 30,000, but a single orbit around the galaxy takes 225 million years. Voyager 1 would need to drift in silence for longer than the age of the dinosaurs just to complete one circuit. And there is no reason it would stop after 1. There is no reason it would stop after 10. There is no reason it would stop at all. The Sun has completed roughly 20 orbits around the galactic center since it formed 4.5 billion years ago. Each of those orbits carried every planet, every moon, every grain of dust in the solar system along for the ride. Voyager 1 is no longer part of that caravan. It separated from the Sun's gravitational influence when it crossed the outer edge of the Oort Cloud, roughly 30,000 years after its mission ended. From that point onward, it orbits the galaxy on its own terms, following a path determined by its velocity and direction at the moment of departure, modified by the gravitational landscape of the Milky Way. That path is not identical to the Sun's orbit. The spacecraft left the solar system at a different angle and a different speed than the Sun moves through the galaxy. Over millions of years, the two paths diverge. Voyager 1 and the Sun gradually separate, drifting apart like two boats launched from the same dock into different currents. After a few 100 million years, they could be on opposite sides of the galaxy. After 1 billion years, the relationship between the spacecraft and its star of origin becomes a statistical footnote, a piece of trivia about an object whose birthplace no longer has any physical relevance to its position. This is the timescale on which Voyager 1's journey truly operates. Not years, not centuries, not even millennia, millions of years, billions of years. Spans of time so long that the galaxy itself evolves around the drifting spacecraft. Stars are born and die. Nebulae collapse into new solar systems. Supernovae detonate, scattering heavy elements across thousands of light years. The spiral arms of the Milky Way rotate and shift, reforming their shapes over hundreds of millions of years. Voyager 1 moves through all of this. A spectator that cannot see, a passenger that cannot feel, an artifact from an era so remote that the civilization which built it might as well be a geological stratum, a thin layer of altered rock on a planet whose surface has been reshaped 100 times over. The question that nags at the edge of this story is simple and unanswerable. How long can Voyager 1 survive as a physical object, not as a functioning spacecraft? That question was answered long ago, as a physical thing, a collection of atoms arranged in the shape of a machine drifting through space. What destroys it? When does it cease to exist? The answer is more reassuring than you might expect, and more disturbing. Interstellar space is extraordinarily gentle to solid objects. There is almost nothing out there to cause damage. No atmosphere to create drag or erosion, no liquid water to corrode metal, no biological organisms to colonize surfaces, no weather, no wind, no earthquakes, no fire. The two primary threats to a physical object in interstellar space are cosmic ray bombardment and micrometeorite impacts, and both operate on timescales so long they almost do not qualify as threats at all. Cosmic rays are high-energy particles, mostly protons, accelerated to near-light speeds by supernova remnants and other violent astrophysical processes. They permeate the galaxy. Every second, cosmic rays pass through every object in interstellar space, including Voyager 1. Over time, they damage materials at the atomic level, displacing atoms in crystal lattices, breaking chemical bonds, gradually degrading polymers and semiconductors. The spacecraft's electronics are particularly vulnerable. Circuit boards, insulation, magnetic tape, the data storage systems that once held the images of Jupiter's Great Red Spot and Saturn's rings, all of these will slowly deteriorate under cosmic ray exposure. Over thousands of years, electronics have become unreliable. Over tens of thousands of years, they become inert. Over hundreds of thousands of years, even the structural integrity of circuit boards begins to degrade, the materials becoming brittle and fragile. But the spacecraft's metallic structure is far more resistant. Aluminum, titanium, and the gold-plated copper of the Golden Record can withstand cosmic ray bombardment for immensely longer periods. The Golden Record in particular was designed with longevity in mind. Its gold plating resists corrosion. Its copper substrate is durable. The grooves encoding the sounds and images are physical etchings in metal, not magnetic patterns on tape or electrical charges in memory chips. They do not fade when the power goes out. They do not degrade when the temperature drops. They persist as long as the metal itself persists. Conservative estimates suggest the Golden Record could remain at least partially legible for 300 million to 500 million years. Some estimates push that figure to 1 billion years or more, depending on the cosmic ray flux along the spacecraft's path and the rate of micrometeorite erosion. Micrometeorite impacts are the other slow destroyer. Interstellar space contains tiny grains of dust, fragments of rock and ice, smaller than a grain of sand, ejected from stellar systems and scattered through the galaxy. These particles are extraordinarily rare, scattered so thinly that a volume of space larger than a house might contain a single grain. But over millions of years, even rare events accumulate. A dust grain striking the spacecraft at a relative velocity of tens of kilometers per second carries enormous kinetic energy for its size. Each impact creates a tiny crater in the spacecraft's surface. Over millions of years, these impacts slowly pit and erode the outer layers of the probe. Over hundreds of millions of years, the erosion becomes significant. Thin components are punctured. Exposed surfaces are sandblasted into rough textures. The spacecraft's appearance changes, scarred by uncountable tiny collisions with the debris of other solar systems. But even this process operates on a timescale that dwarfs human comprehension. Voyager 1 will remain recognizably a spacecraft for millions of years. Its dish antenna, its instrument boom, its Golden Record, all will retain their shapes long after every trace of the civilization that built them has vanished from Earth. The spacecraft will outlast the Roman Empire by a factor of 1 million. It will outlast the pyramids by a factor of 100,000. It will outlast the species that designed it by a margin that makes every other artifact of human existence look like a sandcastle at high tide. And it will outlast the Sun. This is the fact that transforms Voyager 1's story from an engineering narrative into something else entirely. The Sun is a main sequence star with a total lifespan of roughly 10 billion years. It is currently about 4.5 billion years old, meaning it has roughly 5 billion years of stable hydrogen burning remaining. After that, it will swell into a red giant, expanding to engulf Mercury, Venus, and possibly Earth. Then it will shed its outer layers into a planetary nebula and collapse into a white dwarf, a dense, cooling ember the size of the Earth but with the mass of a star. Over trillions of years, the white dwarf will radiate away its remaining heat and fade into a cold, dark object called a black dwarf. The Sun's story ends in darkness and silence. Voyager 1 will still be drifting through the galaxy when the Sun enters its red giant phase. It will still be drifting when the Sun becomes a white dwarf. It will still be structurally intact, at least in part, when the last faint glow of the white dwarf fades below detection. The Golden Record may still carry legible grooves when the Sun's corpse has cooled to the temperature of the cosmic microwave background. The spacecraft will have witnessed none of this, of course. It will be tens of thousands of light years away, following its own galactic orbit, oblivious to the death of the star that warmed the world that built it. But it will exist. A fragment of a species that evolved around a star that no longer shines, carrying music that no one remembers, drifting through a galaxy that has forgotten it was ever there. This is where the story arrives at its deepest truth. Voyager 1 does not die when NASA loses contact. That is the death of the mission, the death of the conversation, the death of the relationship between a spacecraft and the species that launched it. But the object persists. The object endures. The object continues on a journey whose duration mocks the brevity of everything human. We built something whose physical existence will outlast our biological existence, our cultural existence, our stellar existence. The thing we made will outlive the star we were born under, and it will do so in perfect, absolute, unbreakable silence. There is a temptation, when confronting this fact, to find comfort in it, to say that Voyager 1 is a legacy, a monument, a message in a bottle that proves humanity once existed. And it is all of those things. The Golden Record was designed explicitly as a testament, a calling card left in the cosmos for whoever or whatever might find it. But the comfort dissolves when you sit with the timescales involved. A message in a bottle implies a reader, a monument implies a visitor, a legacy implies an inheritor. Voyager 1 will almost certainly have none of these. The probability of another civilization finding the spacecraft in the vastness of interstellar space is so low that it rounds to zero. The galaxy contains an estimated 100 to 400 billion stars. The rare stellar encounters that do occur, separated by tens of thousands of years of empty drifting, offer no meaningful chance of interception. Even if every star the spacecraft eventually passed hosted a spacefaring civilization actively scanning the sky for incoming artifacts, the chance of detection would be negligible. Voyager 1 is too small, too dark, too cold, too slow. It emits no radiation. It reflects almost no light. It is a mote of dust in an ocean of darkness, indistinguishable from the countless other motes of natural debris that drift between the stars. The Golden Record will almost certainly never be played. The greetings in 55 languages will almost certainly never be heard. Beethoven's String Quartet No. 13 will almost certainly never ring out in an alien chamber. The whale songs, the thunder, the laughter of children, all encoded in analog grooves on a gold-plated disc, will almost certainly spend eternity in silence. The bottle will drift forever. The ocean has no shore, and there is no one on the other side waiting for mail. This is not a tragedy. It is something stranger than tragedy. It is a confrontation with scale. Human beings evolved to operate on timescales of days, years, decades. Our emotions are calibrated to human lifetimes. We feel grief when something ends after 70 or 80 years. We feel awe when a building survives for 1,000. But Voyager 1 operates on timescales that are not merely longer than human experience. They are categorically different. They belong to the domain of geology, of stellar evolution, of galactic dynamics. In that domain, human emotions lose their footing. Grief does not scale to 1 billion years. Awe does not encompass a galactic orbit. The feelings we bring to Voyager 1's story are real and valid, but they are the feelings of a species confronting a timescale that was never meant for feeling. What we are left with is something quieter than grief and larger than awe, a recognition. Voyager 1 will continue, not because it chooses to, not because it was designed to, but because nothing will stop it. The galaxy does not contain a mechanism for halting a small metal object moving at 17 kilometers per second through near-perfect vacuum. The spacecraft is not immortal. It will eventually be destroyed. A micrometeorite impact of sufficient size, a gravitational encounter close enough to a star to fling it into a destructive orbit, the slow atomic erosion of cosmic rays over timescales longer than the current age of the universe. Something will end it. But probability favors an immensely long existence, billions of years, perhaps tens of billions. The spacecraft may still exist, in some degraded but recognizable form, when the Milky Way and Andromeda complete their merger, roughly 4.5 billion years from now. It may still exist when the last red dwarfs in the galaxy exhaust their fuel, trillions of years from now, and the cosmos enters an era of darkness populated only by black holes, neutron stars, and cooling stellar remnants. In that dark future, Voyager 1 would be one of the oldest manufactured objects in existence. Not because it was built to last, but because interstellar space is the gentlest environment in the universe. A museum with no visitors, no curators, and no closing time. The spacecraft drifts through it the way a fossil drifts through stone, preserved not by intention but by the absence of anything that could destroy it. We launched Voyager 1 to study Jupiter and Saturn. It did that in 3 years. Everything since has been an epilogue that grew longer than the story it followed. The planetary mission lasted from 1977 to 1980. The interstellar mission will last until the mid-2030s. The silent journey that follows will last until the physics of erosion and probability finally catch up with a tiny metal object in the emptiness between stars. 60 years of purpose. Then, billions of years of drift. The ratio is so lopsided that the purposeful phase effectively disappears. If the entire existence of Voyager 1 were compressed into a single 24-hour day, the active mission would occupy less than 0.002 of a second, a duration too short for a human eye to register as a blink. The rest of the day, all 23 hours, 59 minutes, and 59.998 seconds of it, would be silence. This is the real answer to the question we have been asking. The final place Voyager 1 will ever reach before it dies is not Gliese 445. It is not the Oort Cloud. It is not the edge of the heliosphere. The final place Voyager 1 reaches before it dies is the mid-2030s, somewhere around 175 to 180 astronomical units from the Sun. When the last watt of usable power drains from its radioisotope thermoelectric generators and the transmitter falls silent, that is where the mission ends. That is where the death occurs. Everything after that, the Oort Cloud, Gliese, 445, the billions of years of galactic orbit, all of it happens to a dead spacecraft. A spacecraft that is still moving, still intact, still carrying its golden record, but dead in every sense that matters to the beings who built it. The final place before death is not a dramatic waypoint in the cosmos. It is a quiet patch of interstellar space, unremarkable in every way, distinguished only by the fact that it is where a small machine from Earth finally ran out of warmth. The drama is not in the location. The drama is in the continuation. The fact that motion does not require life. The fact that the journey outlasts the traveller. The fact that the farthest, loneliest road in the universe is walked not by the living but by the things the living leave behind. Somewhere in the mid-2030s, a signal will arrive at DSS 43 in Canberra. It will be the faintest whisper the antenna has ever received. It will carry a few final bits of data about the magnetic field strength in a region of interstellar space no other instrument has ever measured. And then the next scheduled transmission window will open, and the antenna will listen, and nothing will come. The engineers will wait. They will check the frequencies. They will adjust the receivers. They will wait again and again. And eventually, someone in a quiet room in Pasadena will note the time and write the entry that closes a logbook opened in 1977. Mission ended. Signal lost. Spacecraft presumed operational but uncommunicative. Final confirmed distance from Earth. Final confirmed velocity. Final confirmed heading. And 15 billion miles away, in a silence no human ear will ever experience, a small metal object will continue moving at 17 kilometers per second toward nothing in particular, carrying a golden disc that holds the sound of a mother kissing her child, the first movement of Beethoven's Fifth Symphony, and a greeting in ancient Sumerian that translates roughly to, "May all be well." The spacecraft will not hear the greeting. The star it is approaching will not hear the greeting. The galaxy will not hear the greeting, but the greeting will exist, etched in gold, moving through the dark, for a very, very long time. The mission dies. The journey does not. And that may be the most unsettling thing humanity has ever built. Not a machine that can cross the solar system. Not a transmitter that can whisper across 15 billion miles. But an object whose silence will outlast every sound we have ever made. Whose motion will outlast every step we have ever taken. Whose patience, if patience is the right word for something that feels nothing, will outlast the star that gave us life. Voyager 1 is not going somewhere. Voyager 1 is going, and it will not stop. Long after the last voice that could have called it home has gone quiet, the spacecraft will still be out there, still crossing, still carrying its golden cargo, still moving through the dark at 38,000 miles per hour. Not toward a destination, just away, quietly, permanently. into a silence so vast it will outlast everything we know.